Hey, welcome to week 15 of the ACT Math Prep course. We're going to get started with week 15, which is all about trigonometry. All right, so trig for short. Just one thing, a reminder, all right, is that when we've got a right triangle, remember it has to be a right triangle, and we've got this angle theta, we can label these sides as opposite, adjacent, and hypotenuse, okay? So we just want to remember that the sine of the angle is the relationship between the opposite and the hypotenuse. Cosine of the angle is the ratio between the adjacent side and the hypotenuse. And the tangent of the angle is the opposite over the adjacent. Okay, now I'm going to introduce three more here that we need to talk about from trig. It's the cosecant, abbreviated CSC. So cosecant is basically 1 over the sine. So whatever the sine is, you do 1 over that. Okay. The secant is 1 over the cosine. And then cotangent is 1 over the tangent. So remember, it's dumb, but whoever invented this made a mistake. Sine goes with cosecant. Sine should have gone with secant, right? Sine, secant, those S's make sense. And then cosine, cosecant makes sense. But for whatever reason, they switched it on us. And that you have to just remember that sine goes with cosecant, cosine goes with secant. And of course, tangent goes with cotangent. That one actually makes sense. So what happens when you do 1 over what already is a fraction, right? This is 1 over a sine, and sine is just a fraction. So when I do 1 over a fraction, what happens is we flip the fraction and multiply, okay? So what happens is, really, the cosecant is just going to be the hypotenuse divided by the opposite, right? You just take this opposite over hypotenuse and you flip it upside down. So that means that the secant of the angle is going to be the hypotenuse divided by the adjacent. Again, what we're doing is we're taking cosine, which is adjacent over hypotenuse, and we're flipping it upside down. So what does that mean cotangent is going to be? Well, it should be then the adjacent over the opposite. So kind of the inverse, the reciprocal, if you will. Okay, so these are the two things that are kind of new. We talked about sine, cosine, and tangent in geometry and how to solve for right triangles. But this is a little new, and this is something you definitely want to put to memory. Okay, so I had this whole thing planned for the unit circle. Remember, unit circle is just a circle that's centered at 0, and we talk about an angle formed, and then we have this x and y coordinate, which is our cosine and our sine, and there's all these things going on. It's just a huge mess, so I've simplified that for you, and we're going to talk about just ways to use your calculator to come up with these things. So first of all, let's get into this a little bit. When I say an angle, I'm talking about this theta right here. So theta can be measured in degrees, or it can be measured in radians. And radian is just a different way to represent an angle. It's actually a sort of an arc length of the radius. And since 2 pi radians fit around a circle, remember from the formula circumference equals 2 pi times r. So there's 2 pi of these radius distances around the circle. We can measure this angle formed as we sweep around the circle in terms of pi. So if we go all the way around, we say that's a measurement of 2 pi. Halfway around is pi, and all these fractions of pi. We use fractions of pi because they're easier, they look nicer, right? Pi over 2 looks better than what it really is, which is what 3.14 divided by 2 is like 1.56832 blah blah blah. This looks cleaner. We don't want to use this instead. Okay, so here we go. This is the idea of going from degrees to radians. So if you want to go from one to the other, we can convert. Okay, so we're going to convert from degrees into radians. Remember, they're both angle measurements, but a lot of the times on the ACT they say how many radians is 84 degrees, whatever it is. Okay, so here's how you do it. All you do is you multiply when you're going from degrees to radians. Think about like conversions. When you're in degrees, you want to end up in radians. Remember, degrees is in degrees and radians is in radians. So you need this multiplier to change, and what we want is we want degrees on top and radians on bottom. Now, what you may realize, you may not realize, is that pi radians is the same thing as 180 degrees. So this is your conversion rate, pi and 180. They're the same thing. So if you multiply by pi over 180 or 180 over pi, what you're going to do is just change it without really changing the angle. So here we go. If we're in degrees, we want degrees to cancel. So that means we want to put the degrees on bottom and the radians on top. So all you got to do from degrees to radians is multiply by pi over 180. So let's look at an example. Let's say it says 74 degrees equals how many radians? Well, 74 times pi over 180. Now what happens is, remember this is a fraction in disguise, so you multiply across the top. We get 74 pi over 180. This is how they always frame it. They put the number on top with the pi and then the number on bottom. So really all we have to do is reduce that fraction 74 out of 180. So 74 divided by 180. What this is going to do is give me a decimal. And then if I hit math, enter, enter, it's going to give me the reduced fraction. So in reality, instead of 74 over 180, I should say 37 over 90. So 37 pi over 90. That is the radian measure. Okay? So it's real simple. Degrees to radians, you multiply by pi over 180. Again, remember, we're in degrees. We want to end up in radians. So remember, degrees cancels with degrees, and this leaves me with radians. Because this is 180 degrees. I guess that's not a good way to write it. Let me write it like this. This is radians, and this is over degrees. So the word degree cancels with the word degree and leaves me with the number of radians. Okay? So just, if you're in degrees, put degrees on bottom to cancel. All right. What if we're going from radians to degrees? Okay? Same thing. We're in radians. We want to multiply by radians on bottom and degrees on top so that radians will cancel and leave us with degrees. So whatever it is, degrees, remember that's 180 over radians, there's pi radians in 180 degrees. So that's it. Just multiply by 180 over pi. So as an example, if it says 2 pi over 3 radians equals how many degrees? Well, here we go. 2 pi over 3 times 180 over pi. Now what's cool is the pi cancels because one on top, one on bottom. And then we just multiply 2/3 times 180. And I get out my calculator. I say, okay, 2/3, all right, times 180. Gives me 120 degrees. So that's it, 120 degrees. Okay, super duper simple. All right, and just a reminder of this picture of what's going on here. Like for example, 120 degrees, right? That would be right here, 120 degrees. It's this sweeping angle right here. Well, that is also 2 pi over 3 radians. So just remember, radians and degrees are both a measure of an angle. Okay? All right, pretty straightforward. And again, we like using our calculator to help make things simple. So here's really how we're going to make things simple. So instead of using the unit circle to memorize all these values, right, which you're supposed to have memorized, you're supposed to have memorized the sine of 30, the sine of 60, 45, 90, 120, 135, all these numbers. You're supposed to memorize all these things. Instead of doing that, we're just going to use our calculator. So if they ask you for the sine of an angle, so this could be in degrees or radians, right? It could say pi over 3. What's the sine of pi over 3? Or it could say, what's the sine of 135 degrees? Whatever it is, we're going to use our calculator. Now, you do have to be careful here, okay? You got to make sure you're in the right mode. So what mode am I talking about? Well, let's look at your calculator here. Okay, right here when I click mode, there's 2 modes. There's radian and degree mode, okay? If you get something like pi over 2, that's a radian. Anything with a pi is always a radian. If it says, 120 degrees, that's a degree measure. So you got to make sure you're in the right mode, okay, first of all. So when we do this, when we type in the sine of whatever on our graphing calculator, we're going to get 5 choices. We're going to get 0, right? It pops up 0. Or it's going to say 0.5, or it's going to say 0.707 or 0.866 or 1. These are the 5 answer choices that you're going to get when it's a normal sign like 30, 60, 45, 90, a nice even number like that, okay? If it's a sign of 47 degrees, of course you're going to get something weird and random, but this is basically the unit circle, and the unit circle has these nice even degree measurements. So what you have to be able to do is recognize these fractions or these decimals and make them into fractions. So 0 is easy. We know 0 is just 0, right? 0.5 is easy. That's 1/2. 0.707, not so easy, and 0.866, not so easy, but 1 is easy. That's 1. Okay? So if you remember from your unit circle, we get these √2/2s and √3/2s. Okay? Now, what's bigger, √2/2 or √3/2? Well, √3 is bigger than √2, and if we cut either of those in half, √3/2 should be bigger. So that means that this 0.866 is really our √3/2, and this 0.707 is our √2/2. So these are the things you have to be able to convert to. So you've got to put to memory, especially these two. 0.707 is √2/2. 0.866 is √3/2. All right? Say that over and over in your head until you get that. Unless you're familiar with the unit circle, you've got to memorize these. Because when I get to my calculator here, all right, I'm in degree mode. So let's say I do the sine of 300 degrees. Negative 0.866. Negative 0.866, that's negative √3/2. Right? 0.866 is √3/2, so negative √3/2. You got to be able to put that into a fraction because they usually almost never will deal with decimals. They'll always deal with this √3/2 or √2/2 or 1/2 or all those things. Now, of course, if you forget those things, you could always do this real quick. You could do second √3/2. You could actually type this into your calculator, √3/2, and get an answer. So you could write this down, like test could start, and you could write √3/2 is 0.866, √2/2 is 0.707, and then go. And then as soon as you need to reference that, you could go back and look at it, okay? That's not a bad strategy either. But I think memorizing it's pretty doable. Okay, so once you've memorized those and you make sure you're in the right mode, that's pretty straightforward. The only thing you got to be careful of is what about tangent? So just remember, tangent is the sine over the cosine. So you could calculate sine and then cosine separately and divide them and get an answer. But really, I'm going to show you in an example, you really only get two choices. You get √3, you get 1, you get √3/3, or you get 0. Those are really your only choices. And just remember that √3 is actually bigger than 0, and √3/3 is less than, sorry, √3 is bigger than 1, and √3/3 is less than 1. This is 1 point something, and this is 0 point something. So when you're working with tangent, you can kind of make sense of that as well. But again, I'm going to show you how to use your calculator for that, so that's no big deal. Also, don't forget, cosecant is really 1/sine, and that secant is 1/cosine, and that cotangent is 1/tangent. So you can find sine and cosine pretty easily with your calculator. Then you just have to use secant and sine. And remember, if you found out the sine is √2/2, and you know you're supposed to do 1 over that because maybe you're doing cosecant, just remember how you deal with that. You multiply by the reciprocal, okay? Instead of dividing, that gives you 2/√2, and then you have to remember to rationalize that. But again, I'm going to show you how to use your calculator to check that pretty quickly, okay? So, all right, let's look at some examples. So what if it says find the value of 3 sine of 3π/4, okay? Find the value of 3 sine of 3π/4. I would go straight to my calculator. First off, don't mess with the 3 times. Just find the sine part first, because remember, that's the part where we know those fractions. So 3π/4. Now, first of all, I'm doing this wrong, and I wonder if you can see why I'm doing this wrong. That's not a fraction or a decimal that I recognize. What could my problem be? It's mode, right? I'm doing a radian measure, and I'm in degree mode. So I need to make sure I go down here to radian and then go back, and I can just retype it in by highlighting it, hitting enter twice. There we go. 0.707, that is √2/2. Okay. So that means that's 3 times √2/2, and then I just remember how to multiply whole numbers and fractions, multiply across the top, 3 √2/2. There's my answer. That's what you'll see on the test, okay? But again, I'm just recognizing 0.707 is √2/2, 0.866 √3/2, and I'm just using my calculator, okay? All right, next example, the tangent of 60 degrees. Okay. So again, I'm going to grab my calculator here. Now I'm in degrees, so I better make sure I go to degree mode. Big important thing there. All right, now tangent of 60. It's bigger than 1. So I know it's that root 3. Okay? But again, I can double check that by actually doing root 3, which would be one of my answer choices. And I see, oh yeah, root 3 is what tangent of 60 is. So if I had done tangent of 30, you would have seen I got a number less than 1. And that's the one that's root 3 over 3. So root 3 divided by 3 gives you that. Okay? So again, we're using my calculator to reason through this. Now, what I meant to show you is that all these answer choices are on here. So really all I got to do is convert these to decimals to figure out which one works. All right? Cool. All right, moving on. All right, so the next thing we're going to talk about is, really quickly, we got to talk about the coordinate plane here. So there's 4 triangles that you can draw. 1, 2, 3, and 4. I'm making them a little different sizes on the bottom just so you can kind of see. Right, this would be your opposite and your hypotenuse, and this would be your adjacent. This would be your opposite, your adjacent, and your hypotenuse. Hypotenuse, opposite, adjacent, adjacent, opposite, and hypotenuse. Depending on where we're at on the coordinate plane, there's these different triangles that could be created. So here's what you have to think about. If I plot the point right here, this coordinate, see how it's a positive and a positive, positive x, positive y to find that location, okay? To find this location, we do a negative and a positive. So this is actually negative and positive. Just thinking about plotting points, negative x, positive y. So when I plot this point, it's a negative and a negative. So both of them are negative. And when I plot this one, it's a positive and a negative. So positive, adjacent, negative. Now, hypotenuse is always positive, okay? Think of it like a distance. It's always positive. Now, the reason I say that is because in these next problems, we're going to refer back to this, what happens when things are positive versus negative. Also, don't forget, like, thinking about your unit circle, which we really haven't talked about much, but that's okay. This is 90 degrees, this is 180 degrees, this is 270, and this is 0 or 360. It can be either one. So they'll say things like, oh, the angle theta is between 0 and 90. Okay, well, you just have to realize that you're in this region here. If you're between 0 and 90, you're on that top right coordinate. If you're between 180 and 270, then you're in this region here, 270. So between 180 and 270 is here. You just have to remember that's the location that we're talking about. Also, they could do radian measures. So remember, this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this could be 2 pi or 0. So they could say something like, instead of 0 and 90, they could say between 0 and pi over 2. What that means is we're between 0 and pi over 2, so somewhere in this region. Okay, that's what they mean by this restriction between here and here. Okay. All right, very briefly, I need to talk about the unit circle for just a moment. The reason I even have to talk about it is because if you use your calculator and you say, okay, when is the cosine of an angle equal to -1/2? It's going to give you one answer when really there's 2 answers. So you kind of have to know what sine and cosine mean in terms of this unit circle. So really, remember, we can talk about these triangles, and sine is actually just the height. Because the radius is 1 in the unit circle, this unit circle has radius 1. So therefore, every length that I make here has length 1. So because here's your angle and sine is opposite over hypotenuse, well, opposite over hypotenuse, if the hypotenuse is 1, you're just really doing opposite. So that just means that the sine is really the height of this triangle, and cosine is this horizontal length. So in other words, at this coordinate here, for this angle that's defined, whatever this angle is, this is going to be cosine and then sine. So basically, when you plot this point from this angle, so you sweep around this circle and this angle measurement, so like at 90 degrees, you're vertical, you can talk about the cosine and the sine. It's basically whatever the coordinate is on this unit circle. So what that means is we're just talking about x and y coordinates on this circle as we sweep around on this angle. So if the angle is between 0 and 90, right, here's 90, here's 0, if we're talking about all these angles in here, you can see that the x is going to be positive and the y is also going to be positive. When you plot that point, right, remember we're centered at 0, 0 here. When you go over and up to plot that point, you're looking at a positive x and a positive y. Okay, now when you plot a point over here, you go to the left and then up. So that means, again, we're still talking about the x value is the cosine and the y value is the sine. What we're talking about here is a negative cosine and a positive sine. Okay, and then of course when I plot a point here, I go left and down. That's going to be a negative cosine and a negative sine. Okay, it's all about where do you plot this point in which quadrant. So negative x, negative y. We go over here, plot a point. This is going to have, again, it's cosine and sine. Sine is the y value. Always think psi y, right? Sine is the y value. So on this coordinate here, when we travel all the way around to this fourth quadrant, we're looking at this angle. It could be something like 300 degrees, right? That's all the way around and gets to this last point. So the cosine of 300 would be positive because we have to travel to the right and then down. So the sine would be negative. So you're looking at basically the x and y coordinates in these quadrants, and it tells you the values of the sine and cosine. Because right here, when is the cosine negative a half? Well, cosine is negative here, right? Cosines are negative here, and cosines are negative here. So what's the calculator going to say? Well, the calculator is going to say, okay, if I do the inverse cosine of negative 1/2, it's going to say, oh yeah, at 120 degrees. So it's thinking right here, at 120 degrees, remember we start here at this angle 0, and we sweep all the way around to 120 degrees. I'm going to draw a new picture here for you. Okay, remember this is the 0, this is the starting point. We travel around 120 degrees, the cosine is negative 1/2 because we travel over negative 1/2 and then we go up to the y value. So you can see that the cosine here is negative. But what about over here? You see how this unit circle has a second point right here, where also to plot this point you'd have to go left 1/2 and then down. So there's two values. So actually in quadrant 2 and in quadrant 3, the cosine is negative. So that's the idea there about the importance of understanding when cosine is positive and when sine is positive and when tangent is positive and all those things. So remember, it's always cosine sine, that's the xy value. So cosine is positive here, sine is positive here. If we're plotting this point, it's negative positive because we go over up. Right here, it is negative negative. And right here, it is positive negative. So cosine is positive in these quadrants, right? Because the x values are all positive here. The sine is positive in this quadrant and this quadrant, because think about it, when you plot points, the y values are all positive up here. Sine is negative down here and down here, because when we plot points down, the y values are negative. That makes sense. And the x values are negative here, so the cosine is going to be negative here. All right. Now, if you remember, the tangent is just sine over cosine. So when I look at positive over positive, tangent is going to be positive here. Okay. Now, even back here in quadrant 3, it's negative over negative. So it's going to be a negative over a negative. That actually makes it positive. So tangent is positive in quadrant 3 as well. What about here? Well, it's a positive negative, right? A positive and a negative. When I do sine over cosine, it's going to be negative over positive. Tangent is going to be negative in this quadrant. And you would see here that tangent is also a negative in quadrant 2. So that's kind of the sign of all these things. They'll ask you these questions where they expect you to know, where is the cosine positive? Where is the cosine negative? Or these little questions where they kind of need you to know that. All right, so let's look at an example here. So an example might be that it'll say find the secant of theta if the sine of theta is 12/13. And then it'll say, let's say 0 less than or equal to theta less than or equal to pi over 2. So what that means is we're between 0 and pi over 2. Okay, I know you can't see that there. Let me rewrite that where you can see it. There we go. So this is just saying we're between 0 and pi over 2. Okay, now between 0 and pi over 2, that's this first quadrant here. This is 0 and this is pi over 2 in radian measure. So we're in this first quadrant, somewhere in here. That's all we know. Okay, so what we do is we draw our triangle. Remember, we always come down to the x-axis from where we go out. And here's our angle theta. It's always the one tucked into the origin. So remember, sine of the angle is the opposite over the hypotenuse. And we just were told that the sine is 12 over 13. Well, then I can label those. Here's my opposite, here's my hypotenuse, here's my adjacent. And then they tell me that opposite is 12, hypotenuse is 13. So we know the lengths of those two sides. But what I need to do is always find the third side. So I can use Pythagorean theorem. The adjacent side squared plus the opposite side squared equals 13 squared. Remember, it's always a right triangle, and we're using Pythagorean theorem. A squared plus b squared equals c squared. C is always the longest side, which is the hypotenuse. If I solve for this, I get 144 plus a squared equals 169. I take away 144, and then I square root. So a squared is 25, so that means that when I square root, I get 5. Now, we should have known that. This is a 5, 12, 13 Pythagorean triple. 3, 4, 5, and 5, 12, 13 are the two that you need to make sure you have under your belt. We should have been able to do that without doing all this work here. We shouldn't have had to do that. Okay? It's okay if you didn't recognize it, but we want to try to recognize it. It'll help save some time. So now that we've got the triangle labeled, now we go find what they're asking for. Well, they're asking for secant. And remember, secant is 1 over cosine. I had to think about it because secant doesn't go with sine, which it should, but secant and cosine go together. So 1 over cosine. Well, cosine is adjacent over hypotenuse. So remember, 1 over that will flip that. So really, the secant is hypotenuse over adjacent. That's what I need. Well, I've got those numbers. I've got 13 is the hypotenuse, adjacent is 5. That's all I got to do. 13/5 is the value of secant. Okay, so that's actually pretty doable. Just got to set up a triangle, label your sides, write down the sides that they give you, use Pythagorean theorem to find the third side, and then answer the question. Okay, that's basically how you do those. Now let's look at another problem. Okay, maybe we'll do a similar thing, but this time we're going to be between pi over 2 and pi. Okay, so remember where that is pi over 2 is here, and pi is here, so we're somewhere in this third quadrant. So I'm going to draw my picture, second quadrant, I should say. I'm going to draw my picture like this. All right, so maybe they say the secant of theta is 5 over 4. Find the tangent of theta. Okay, so here we go. We label theta as the corner angle there. Remember, this is a right triangle. We've got our opposite, adjacent, and hypotenuse. So what do they tell us? They tell us secant is 5 over 4. Well, just remember from our last problem that secant is the hypotenuse over the adjacent because it's 1 over cosine. So when they tell us that it's 5/4, we know that the hypotenuse length is 5, the adjacent is 4. We should also know, sorry, let's make this a negative 5/4. Sorry, let's start the problem over. Secant theta is negative 5/4. The reason that is because it's got to be a negative 4 over 5, because see how we go to the left? Well, that means we're really going negative 4 over. So it's a length, but it's more like plotting a point. Okay, well, this is a 3, 4, 5 triangle. Now this is positive since it goes up. So that's going to be 3, 4, 5. But just remember, if secant is negative, that just means you're going over or down. Either way, one of those numbers could be negative because we're traveling in the left direction, which is negative. Right direction is positive. Okay, so that means that we've got all our sides labeled. Now we just got to find the tangent. So just remember, tangent is opposite over adjacent. So opposite is 3, adjacent is negative 4. So 3 over 4, but it's a negative 4. So negative 3/4 would be the answer there. Okay. Again, it's all about setting up a triangle. Use Pythagorean theorem to find this. Now remember, if you didn't know that was 3, we would say 5 squared, or excuse me, x squared plus negative 4 squared plus or equals 5 squared. And you would use Pythagorean theorem, you get x equals 3. That's where we get this 3 from. Okay, so you can always use Pythagorean theorem if you're solving these, but look out for those 3, 4, 5s and those 5, 12, 13s. They're definitely going to be out there. All right, next topic, law of sines. okay? You use this formula when you want to know or you know. So there's always stuff you know and there's always stuff you want to know. All right, so when you know and you want to know two sides and two angles that are opposite of each other. So meaning, if we've got a triangle and I call this angle A, angle B, and angle C, this is always a side C, side B, and side A. They're always across from each other. If you know A and want to know C and you know the other C, that's what I mean by pairs of opposite sides, okay? Or it could be B and B. But either way, you're going to use law of sines in this case. So here's the formula. Basically, it's the sine of angle A over the length of the opposite side, so little a, should equal the sine of B over little b, which should equal the sine of big C over little c. Now, you only use two at a time, but this is just showing you that they're all three equal. So maybe, you know, let's look at a triangle here. Maybe, you know, this is 7 and this is 6, and this is 35 degrees, and you want to know the measure of this angle right here. This is a perfect case for law of sines. We would say that the sine of 35 degrees over 6, right? Those are my opposite pairs. Those go together. Should equal the sine of x divided by 7. Now, sine of 35 you can use your calculator for. All you got to do then is cross multiply, and you get that the sine of 35 times 7, or 7 times the sine of 35, equals the sine of x times 6. So we divide out the 6, and we get this. The sine of x is this. So if you used inverse sine to kill off the sine, you'd have x, okay? Or if it's just the number on bottom, you'll get it, and you just use your calculator here to find out what it is. So let's just try this one. I'm going to rewrite this. Right now I have that the sine of x is 7 times the sine of 35 divided by 6. And then remember, I'm going to kill off this sine with a sine inverse. So really, I just need to find the sine inverse, because that tells me what x is. Okay? So sine inverse of this crazy looking thing. It's not terribly difficult, right? Let's see, 35 is degrees, right? That's 35 degrees, so I need to make sure that I'm in degree mode, which I am, okay? So sine inverse, so second sine inverse of alpha y equals, that makes a fraction. I want 7 times sine of 35 divided by 6. There we go, 42 degrees, okay? That's how we use law of sines. So just use it when you know two sides and two angles. And a lot of the times they just want you to set it up. They don't even care if you actually get the answer sometimes. Sometimes they just have you set it up. All right, so the next one we're going to do is the law of cosines. Now, technically they could ask you two different versions, but I'm going to just kind of assume that they give you the one that is normally on the ACT. So we're going to use this when you know an angle, when you know an angle and the two sides next to the angle. That's the angle symbol there, okay? When you know an angle and two sides next to the angle and you want to find the third side, okay? You know two sides and you know the angle in between those two sides, you want to find the third side. We're going to use law of cosines. So here we go. The formula is a squared equals b squared plus c squared minus 2ab cosine of a. Okay, so here we go. Here's our big angle A. Here's A that we're usually going to try to find. Here's the B and the C. So you got to know these three, and then you can find that A, little a. All right, so here's an example. Let's say you got a 130-degree angle. We know that this length is 5 and 6, and we want to know the length of that third side. Okay, so here we go. A squared, right? We don't know that third side. But remember, since this is little a and this is the angle A, they're opposite from each other. You always find the angle that's opposite. So a squared, or x squared in this case, since it's labeled x, equals b squared plus c squared minus 2ab cosine of a. Okay? So notice the 5 and the 6 happen multiple times here. So really, I just type this into my calculator. All right, I do 5 squared plus 6 squared minus 2 times 5 times 6 times cosine of 130 degrees. Now I better make sure I'm in the right mode here because this could totally mess me up. I am in degree mode, so I'm good. Okay. Now I've got this extra parentheses here that I need to delete accidentally. All right, delete. Hit enter. 99. Okay. Now something doesn't seem right about that. It doesn't make sense to have a 5 and a 6 and a 99. Well, that's because this is the length of the side squared. All right, 99.567. Now really, I'm going to leave that in my calculator the way it is, and I'm just going to square root both sides. Ultimately, I need to find x, not x squared. So if I square root this answer here, square root the answer, remember that's second minus, I get 9.97. That seems a little more reasonable here. This is 9.97. This is 5 and 6. We've got a big angle making the biggest side across from it. And that's basically law of cosines. Now technically, I suppose they could ask for the angle A, right? They could ask for A, or they could ask for B or something, but usually they're asking for A, this little a. But if they ask for cosine of A, just remember to solve for the big A and then use inverse cosine to kill off the cosine to then find your angle. Okay. All right. Next thing we're going to talk about is graphing trig functions. Okay. We're going to graph trig functions. Okay, so the main ones are sine, cosine, and tangent. All right, these are the three that you got to kind of know without a calculator. So here we go. Sine always starts at 0 and then goes up like this. It also goes backwards, but we're just going to focus on this first little piece here. Okay, so this is what we call a period. It's one full rotation, so up, down, and up. That's a period. All right, so this is pi and this is 2 pi. It always goes from 0 to 2 pi in a normal period. All right, so things you got to know. It starts at 0, 0. That's its initial value, okay? It goes through 0, 0. It has a maximum of 1 and a minimum of 1, okay? This is at a height of 1 and this is down here at a height of -1, okay? But it starts through 0, 0 and then goes up and down and up. Okay, again, you could use your calculator to show that, but this is one you want to kind of try to memorize. Cosine starts up at the top and then comes down and up and down and up and down and up. Okay, so we're going to really focus in on this one cycle here, this period of the top to top. Okay, so it starts at 0, 1, has a max of 1 and a minimum of 1. Okay, and then tangent. This one's a little funky. It has these vertical asymptotes at, I guess this is, well, we'll talk about the centers. The centers are at 0, pi, and 2 pi. Oh, also, I didn't talk about this. This is 0, and this is 2 pi. Could be in degree measures, like 360, but usually we go from 0 to 2 pi. Here's tangent. It kind of comes up like this, and does one of these things. All right, and it's got these vertical asymptotes. So the vertical asymptotes are at pi over 2, 3 pi over 2, etc. But that's what tangent looks like, okay? You need to just be able to recognize these, like, okay, I know what tangent looks like, I know what sine looks like, I know what cosine looks like, okay? Now we can use a graphing calculator to graph the other two, all right? The other three. But what do we want to know here? This thing is centered at 0, 0, and it has these, it's undefined at pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay, it's got these vertical asymptotes. So every pi, it's centered, and every pi, it's got a vertical asymptote. Okay, so let's actually take a look real quick at graphing trig functions. So let's say we've got a graph here, and I want to graph sine. Okay, sine of x. And then graph it. It looks totally funky, okay? First of all, usually on the ACT, we're dealing with angle measurements that are in radians. So usually you want to be in radian mode, okay? And let's try this again. There we go. There's kind of our sine. Now, one thing to think about is you can adjust the zoom for trig functions, right? Zoom 7 is zoom trig. And when you do that, it does it nice and pretty. Now, what it does is, see these little marks? Right before we did that, if I go back to zoom standard, see how these marks are spread out a little differently? When I go to zoom 7, it makes it nice and easy. Like, look, the very top is right where this mark is. This middle is right where the mark is. What it does is it adjusts the table for us, okay? And see how at 0, this is actually pi over 2, or pi over 4. Let me think, pi over 3. It basically goes by pi over 6s. So every one of these is pi over 6. You can see when I go down here to pi, which should be 3.14, there's pi. So at pi, it's 0 again. And when I look at the graph, I can see that. This is 0, this is pi, it's 0. And then at 2 pi, it's 0. At negative 2 pi, negative 4 pi, all those things. So at every pi, it's a 0. Okay, so one thing you can realize is zoom 7 is a great way to be graphing when you're doing trig. It's a great starting point, okay? Also, you can adjust your table set. So table set, it starts at this weird number and changes by this weird number, and that's okay. What it is it's pi's. So you want to start at 0 usually, and you want to go up by, I usually do pi over 6. So pi over 6, or pi over 12 is another good one. Pi over 12 is safer. That's that 0.2. That's what they were doing. So do your table set to, or your change in table to pi over 12. Then when you look at your table, you can see all these normal values, right? Half, remember these, my pi over 2s, remember the 0.707 and the 0.866, those are all popping up, which is good. So anyway, this is just a good starting point, this pi over 12. It helps you with a lot of things. Now, when you're looking at the graph, okay, there's lots of things we can do. We can find the maximum and where it occurs. So I can do second calculate maximum. All right, this requires a left and a right bound. So I go to my maximum and then I set a left bound. So I go over to the left and I hit enter. Then I go over to the right and I hit enter. Then I hit enter again, and it's going to say, oh, at 1.57, it's at a height of 1. Well, 1.57 is a special number, okay? It is pi over 2, and I can show you that. When I take pi and I divide it by 2, I get 1.57, okay? So 1.57 is what I get for pi over 2. So that's really what pi over 2 is. So anytime your answers on the ACT are in pi over 2 or 3 pi over 2 or whatever, just remember you can always check that decimal value by typing it into your calculator, okay? All right. So that's basically how you use your calculator, how you can find the maximum and the minimum. And actually, once you're in the Windows Zoom like that, you can actually use trace. Hit the trace button. It actually, usually trace is horrible, but this actually works pretty well. There's at pi, we're at 0. See how the y says 5.89 times 10 to the negative 10th? That's really just 0. Okay, and there we go. There's my maximum at negative, or my minimum is -1. It happens at 4.7, which is 3 pi over 2. All those, when you're in Zoom Trig, trace actually works pretty well. Usually I avoid trace at all costs, but trace works well when you're in Zoom Trig. Okay, so here we go. Let's continue on. Let's talk about the period. So remember, we were talking about the period is a full cycle of this function. So from start to finish, all the way through. Okay. So the period is a full cycle of a trig function. So when I say that, it's either the top to top, or it's the bottom to the bottom, or it's the middle to the middle that makes sense. And let me talk about that real quick. So like if you've got a function like this, we're at the middle, it's not to the next middle because it hasn't gone through a full cycle. It's the middle to the middle that comes back around. So this distance here is the period. Okay, this is our period, P. So it could be the top to top though. You can measure it from the top to the top. That's also the period. It's the same distance. Or you can measure from the bottom to the bottom. Either way, you're going to find the same length there, that same length So from top to top, bottom to bottom, or the middle to the middle, that makes sense. So if we're looking at the tangent, right, you could do the distance from this middle to this middle. Or you could do, from anywhere to the same point. Okay. All right, so there's actually a formula for this. It's 2 pi over b for the period. And b comes from the standard form of any sine or cosine is this, bx minus c plus d. So the coefficient of the x, or it could be theta, is going to be what your b is. So if you had something like sine of 6 theta, 6 would be your b. So in this case, it'd be 2 pi over 6, which is pi over 3. Okay, and I can actually show you that on here. If we graph the sine of 6x, you would see that your period, so the distance from the bottom to the next bottom, the second bottom, is going to be pi over 3. And I can look at that with my table. I can see from here to my second one, see how I've gone through a full cycle. I start at 0, I go all the way to the top, I go back to the middle, down to the bottom, back to the middle. This is my distance. So pi over 3 is 1.04. Just to check that, yeah, pi over 3 is 1.04. So that makes sense there. So just remember that formula, 2 pi over b, where b is the coefficient here. Now what if we had cosine of 1/2 theta? Well, you do 2 pi over 1/2. And remember what we do is we flip that fraction over and multiply. So you'd actually have 4 pi. So that would actually make it more spread out. I can show you that again on here. If I do cosine of 1/2 x, graph it, you can see, oh yeah, it slows down. So we'll go to zoom trig, there's our thing. So from the top, or yeah, we'll go from, well, I can do bottom to bottom actually. See down here, all the way to down here, that's the period from the bottom to the bottom. But again, I can look at my table and really see it. So let's say from the height of 1 all the way, when do I get to be a height of 1 again? All the way until, whoa, it's a long ways. I'm still not at 1. There we go. So 12.5 is the distance to go from the highest to the next highest. Okay, and that of course is what 4 pi is. 4 times pi is 12 point whatever. Okay, so that's basically how you can use the formula to find the period of a trig function of sine or cosine. Now be careful, tangent's period is pi over b, not 2 pi over b, it's pi over b. So you got to be careful there. But you can always use your graphing calculator to reason through the period. It's the distance from the center to the next center after it goes through a full cycle, or top to top, or bottom to bottom. You can just use your graphing calculator. Just make sure you're in that trig zoom mode. Okay, so next thing we're going to do is talk about transformations of trig functions. Okay, so remember, we're gonna, with any transformation of a function, we start with the most basic graph and then we change it from there. So we're gonna start with something like sine x, okay? And remember, from the graph of sine, it starts at 0 and does this. Height of 1, low of -1. Okay, so what happens if I do now 4 sine x? Remember, this is a multiplier, and multipliers make things taller. They vertically stretch things. So instead of being at a height of 1 here, I'll do this in a different color, we're now going to be at a height of 4. It still goes down here like this, but now we're 4 tall and 4 down. So now we're going to -4 to +4. Now what that affects is my amplitude. My amplitude is the distance from the center to the top. So my amplitude here would be 4. Okay, normally the amplitude of a sine function is 1. It's the distance from the center to the top. So the amplitude is now 4. Does it affect anything else? Did this 4 affect the period? No, the b didn't change. The b was 1. Now the b is still 1. So remember, 2 pi over b, which is 1. So the period is still 2 pi. The period didn't change. All right, what's the max? Well, the max now is 4. And the min now is -4. So these things change. The amplitude and the max and the min are now different, okay? But the period stayed the same, and all that stuff stayed the same, okay? So let's look at another example. Let's look at y equals sine of 2x, okay? Now remember, multipliers always change things by stretching or shrinking, but when it's with the X, it's left or right stretch or shrink, okay? Remember the story when you're at the mall with your ex, they get the ice cream thrown at you, you dodge it left or right. When you're not with your ex, you're in a relationship, it's an up and down. So this number here affects the up and down, whereas when it's here, it affects the left and right, which of course is going to affect our period, which makes sense. So first of all, let's graph this thing. So remember, normally sine goes like this, and it takes 2 pi to go through a full cycle. So here's 0, here's 2 pi. I'm going to graph this one in a different color. What happens to the 2? It affects the period, right? So 2 pi over 2 is now the period, because b is 2. Well, when you cancel that, you realize that it takes just a pi to go through the full cycle. So it actually goes through the full cycle in half the time, okay? When you do a multiplier with the x, it actually works in opposite ways. This thing actually horizontally shrinks the function to where it happens twice as much in the same amount of time. Now, what's the height? The height is still 1, the lowest is still -1. So the max is still 1, the minimum is still -1. What's the amplitude? The distance from the center to the top. It's still 1, right? That shrinking didn't affect that. What it did affect was the period. The period is now pi. So that's what changed in this function. So when we have that 2x in the middle, or with the x, that 2 will shrink it and to change the period. All right, let's try another one. First, we're going to again start with sine x, but this time we're going to do sine of x plus 3. Okay, so just a reminder, normal sine takes 2 pi to go through a full cycle. There's starting at 0. Remember, it's at a height of 1 and a low of -1. Now, what does this plus 3 do? Right? When we add or subtract numbers, it shifts. So it either shifts it up, down, or left or right. Well, this one is not with the x, right? Because it's not in the sine argument. It's actually off to the side. Usually you might see a parentheses like that. But anyway, this goes up 3. It shifts everything up 3. Okay? So this point here goes up to here at 3. And I'm going to run out of room here. Maybe I'll just graph it down here. So 1, 2, 3. It starts at 3 now. It still goes up 1 and down 1 like this. It still takes 2 pi to go through a full cycle. But what has changed now? What's the amplitude? The amplitude is still 1. Okay, the period is still 2 pi. What's different now is the max and the min. So when you add or subtract the number at the end, it affects the max and the min. The max here is now at 4, and the min is now at 2. Because now it's centered, right? It's sort of the central line is at 3. So it's 1 up, 1 down. Okay, now remember, all this can be done on your graphing calculator. If I were to graph sine of x plus 3. Okay, if I were to graph it like that, I would be able to tell that. I can say, oh yeah, it goes up to 4 and down to 3. That's pretty easy. So graphing these are pretty easy too, but sometimes you can do it without even having to graph stuff. All right. All right, so real quick, I did want to mention another transformation. When you have a negative sign in front, that could be a negative anything. Like let's say I have negative sine of x, okay? Remember, again, this is normal sine of x, goes all the way to 2 pi to 0, 0 to 2 pi. I mean, it keeps going, but that's like one cycle. So what happens when you have a negative sign is basically anything that's up at 1 gets flipped down to -1. These zeros actually stay the same. And see how this is down here at -1? Well, it gets flipped to the other side to +1. So what it does is it flips it upside down. So it reflects it across the x-axis. So when you see this negative in front, it's going to do that. Now remember, if you have -3 sine x, remember what we said, that number in front was a multiplier. It affects the amplitude or the stretch factor, the vertical stretch factor. That would, of course, do the same thing this one did, but it would make it 3 times as tall. So it would have a maximum of 3, a minimum at -3. But of course, we start by going down instead of going up like it normally does, because that negative sign flipped it. So the negative flips it, the 3 stretches it vertically, and that's how the negative sign works. What if you graph y equals sine of x minus pi? Okay? Remember, this pi is going to shift it left or right, and it's going to be backwards. It's actually going to shift it right pi units. So the whole thing of sine is going to now shift over to pi. So now it's going to actually start here. I'll do this in green. It's going to start here, and it's going to go like this. So remember, this is actually going to look like this. So that's what sine of x minus pi will look like. It just shifts every point, right? Every point gets shifted pi units to the right. So just be aware of that. Now that doesn't affect the period, doesn't affect the amplitude. It just affects it doesn't max or min. None of those things get affected. Just kind of like your starting points. All your points get shifted over a little bit. Okay. All right. So the last thing we're going to kind of talk about is solving trig equations. All right, so really when we solve an equation, we're looking for the value of the variable that makes the equation true. So we're usually going to be finding the value of theta or x that makes the equation true. Okay? So let's start with something really easy. Okay? The sine of theta equals negative root 2 over 2. Okay? When is the sine of theta equal to root 2? Well, what angle, that's what we're looking for. What angle gives us the sine of root 2 over 2? Okay, there's actually two answers, and what you kind of need to be able to do is think about this unit circle and think about, remember, sine is the y value. So somewhere along here, there's a y value that's this same value here and here. So whatever this angle is, and also whatever this angle is, will give us those two negative sine values. So there's two places. Now here's the easiest way to do it. You just use your calculator. Or you could use guess and check. Like if your answers were, 30 degrees, 90 degrees, 225 degrees, 260 degrees, whatever, you could just plug it into your graphing calculator, right? We're in degree mode since we're looking at all degrees, so I need to make sure I'm in degree mode. And then I would just say, okay, let's find the sine of, what was our first choice? 30, sine of 30. Is that going to be negative root 3 over 2? No, it's a half. Then we do the next one, sine of 90. What's that going to be? Nope, it's not. So we're just guessing checking here. We're saying what value of x or theta here will give us that, right? So what about sine of 225? Negative 0.707. 0.707 is root 2 over 2, so that's the one. Okay, so we would say, okay, it is value C. All right. Now, a lot of the times there's multiple ones because 315 would actually work as well. Okay. But just be aware that that's the basic idea. Now, I could do sine inverse. Okay. I could do sine inverse. I could take the sine inverse of both sides because remember, sine inverse kills off sine. So as long as I do the same thing to both sides, I should get it to work. So what I do is I do sine inverse of negative root 2 over 2. And it says negative 45 degrees. What you got to recognize is that this angle here, 315, is also negative 45. So that's where it kind of gets weird. You have to really know your trig stuff. But you can either travel in this direction in positive angles or travel this direction in negative angles. But negative 45 degrees is 315 because this is 360 all the way around. If you back off 45, you're at 315. All right, so just a couple different thoughts there on how to solve a basic sine and cosine one. All right, so what about this one? The cosine of 3 theta minus 10 equals a half. Okay, well, first of all, we want to know this right here. The cosine of something equals a half. Well, we know the cosine of what equals a half. If you either know your unit circle or you can do cosine inverse. So cosine inverse of 1/2 is 60 degrees. Okay, so we know that the cosine of 60 is 1/2. So what that means is whatever's inside this parentheses needs to equal 60. Okay, you see how I used cosine inverse to find what this had to be? I used cosine inverse of both sides. Okay, so that's how I found that it was 60. From there, you just solve for the angle. So I'm going to add 10 to both sides. That gives me 70 equals 3 theta. Divide by 3, we get 70/3, or whatever that is a decimal, either way. So sometimes you have an expression inside the parentheses, and all you got to do is know what that expression has to equal by using the inverse trig function, because remember, inverse functions give us the angle, what's inside the parentheses. You set it equal to that angle, and then you solve from there. Okay? All right. So What if you have something like this? Another example, cosine squared of theta plus cosine theta equals 0. Okay, here's what you got to remember. What if instead of cosine of theta, we called it x? So what if cosine theta was just x? What would we have? We'd have x squared plus x equals 0. We could solve that. What would we do? We'd factor out a common factor, which leaves us with x plus 1 equaling 0, right? Remember, you could always check by distributing back to make sure you get what you started with. Then we do the zero product property. If two things multiply to be 0, either of them could be 0. And then we say, okay, x is 0 and x is negative 1. There's my solution. Well, we're going to do the same thing, but we're going to use cosines, okay? So we're going to factor out a cosine. See what we did there? They both have a common factor of cosine. Remember, cosine squared is really cosine of theta squared. Okay, that's the same thing as cosine of theta squared. So what we're doing is we're just realizing there's cosines there and there's cosines there. Pull it out. It leaves one cosine here. It leaves just a 1 there. So we get this right there. Okay, then we use zero product property. So the first thing could equal 0, or the second thing could equal 0. And either way, we could use inverse cosine and then take away 1 here, and then use inverse cosine here, and we'd make it work. Okay, so we just do inverse cosine of 0. Inverse cosine of 0 tells me, oh, that happens at 90 degrees. And then inverse cosine of negative 1, it tells me my answer is 180. Okay, so just remember to use it as, just pretend like how would it work with x? You can always do it with cosines as well. So just imagine, how would I do it if they were x's, and do the same thing with cosine. Now, a couple thoughts here. You could solve this using your graphing calculator. These are equations, right? We could graph the left side and the right side. Cosine of x squared plus cosine of x. Right? What we're doing is we're graphing the left side. Here's the left side, and then we graph the right side, which is 0. And we're going to find the intersection. All right, now I'm going to use zoom trig here because this thing's out of whack. There we go. There's my solutions right there. Boom, 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 boom. So if I do second calculate, intersection number 5, enter, enter, and then get close to one of these. There we go, 90 degrees. Right? Second, calculate number 5, enter, enter, and then get close to the next one. 180 degrees. Right? The next one's going to be 270. So I can tell, now remember, I'm in degree mode right now. That's why my graph, when I did zoom trig, it was in degrees. Now, if I'm in radian mode, it'll actually look the identical graph. Well, it should look like the identical graph. Once I hit zoom 7, there's the identical graph, but now it's all in radian measures. So if I do the same thing, number 5, enter, enter, and then get close to this one, hit enter. There's my 1.57. That's pi over 2. Okay, so if you're in radian mode, you can still do that. It'll still work, but just remember, once you change modes, to go back to zoom 7, that trig zoom, to reset your graph, because the window will be all messed up. All right, lastly, great time for guess and check here, okay? You can always take those answers, there's only 5 of them usually, plug them in for theta. So if you said, okay, theta was 90, 180, 270, what if it said 45 and 30? Right? These are maybe your 5 choices here. All right. Well, all I do is go to my calculator. Remember, what I'm saying is that the cosine of, remember my formula was this: cosine of theta squared plus cosine theta equals 0. So I want the whole thing to equal 0. So I just go to my graphing calculator and I say, okay, the cosine, let's make sure I'm in the right mode. I need to be in degree mode since my answers are in degrees. All right, so cosine of 30 squared plus cosine of 30. If it's not 0, it's wrong. It's not 0, it's wrong. Remember, I can go up here and hit enter and it retypes it in. Sometimes this saves you a little bit of time. My other option, right, was 45. So I do 45. Oops. So I change this to 45. Change this to 45. And I realize it's not equal to 0. Then I go up to 90, right? This really, I could do this in under a minute, and you get a minute per problem. So this is, guess and check's a great way to go here. I get 0. So that's my answer. 90 is my answer. Okay, so guess and check's a great strategy here. Or you can use your calculator to find the intersection points, but whatever it is, we've got to be comfortable with those things, because those things get us out of pickles, and we don't want to be in pickles. So those kind of things are things we have to make sure we're good at. Okay, all right, well, that's all I have for today. Appreciate you guys being here, and we will see you next time.